Big Bang. Ooh, the birth of space-time energy.
The Big Bang is widely regarded by scientists as the leading theory explaining the origins of the universe. This theory describes how everything was created, from stars and planets to all living beings, including us.
14 billion years ago, and we have no idea what happened before it.
Despite the somewhat playful name, the Big Bang accurately captures the essence of this monumental event. Initially, the universe was nothing more than densely packed particles squeezed into a space tinier than a pinhead. From this single point, an enormous explosion of matter occurred, which we now call the Big Bang. That's just a brief overview of what transpired over billions of years. However, despite the enduring popularity of the Big Bang theory, nearly every prediction it has made has been increasingly challenged by more accurate data. Because of this, when NASA launched the James Webb Space Telescope, the largest and most powerful space telescope ever built, scientists anticipated that its data would support the Big Bang theory.
Yes, we expect James Webb to make great discoveries. And so I gave my best professorial reply.
Unfortunately, after just a year in space, the Webb telescope is astonishing scientists with its incredible observations of the universe. Its latest images are challenging the existing research, as they include photos of galaxies that formed shortly after the Big Bang, among other surprising revelations. These findings may call into question everything scientists thought they knew about the origin of the universe. Join us as we delve into the James Webb Telescope's remarkable discoveries that might even shed light on the universe before the Big Bang. The tale begins with an extraordinary glimpse of the universe through the eyes of the James Webb Space Telescope, offering a perspective unlike any seen before. Astronomer Rohan Naidu was relaxing at home with his girlfriend when he made a remarkable discovery. Late one night in July 2022, as Naidu's algorithm analyzed early images from the James Webb Space Telescope, JWST, it unearthed something extraordinary. Naidu suddenly found himself fully engaged as the algorithm identified an object of inexplicable massiveness, dating back to a mere 300 million years after the Big Bang, making it older than any galaxy previously observed. The discovery stunned Naidu so much that he immediately called over his girlfriend, exclaiming, "This might be the most distant starlight we've ever seen." After sharing the thrilling news with one of his collaborators through a flurry of excited messages filled with exclamation marks, Naidu and his team got down to business. Within days, they published a paper on the newfound galaxy, affectionately named Glass Z13. The news spread like wildfire across the internet, capturing global attention. Naidu expressed how the revelation of this galaxy, mere weeks into JWST's full operations, surpassed even the wildest dreams of astronomers. The JWST, hailed as the most massive and potent observatory ever sent forth from Earth, was constructed with the aim of fundamentally reshaping our comprehension of the cosmos. Positioned 1.5 million kilometers away from earthly disturbances and cooled to nearly absolute zero by its vast sun shield, roughly the size of a tennis court, this telescope boasts a colossal segmented mirror and incredibly sensitive instruments meticulously crafted to unveil hitherto unseen intricacies of cosmic origins. This period is relatively uncharted territory, occurring just a few 100 million years following the Big Bang, when the earliest stars and galaxies began to form. The precise mechanics of this phenomenon hinge on intricate physics, encompassing factors such as the enigmatic roles of dark matter and dark energy, as well as the intricate interplay between starlight, gas, and dust, which remains largely unexplored. With the JWST providing insights into galaxies from cosmic dawn, cosmologists have the opportunity to scrutinize their understanding of these fundamental phenomena, This can either affirm the accuracy of their prevailing consensus models or unveil areas of uncertainty that may lead to significant breakthroughs. Originally, such observations were anticipated to be a gradual process. Early projections suggested that the first galaxies would be dim and relatively small, with JWST possibly identifying only a handful of intriguingly distant candidates during its initial explorations. Things didn't unfold as anticipated. Almost immediately after the scientists behind the telescope released its initial images of the remote universe, astronomers like Naidu from the Massachusetts Institute of Technology began uncovering countless galaxies within them. These galaxies surpassed all expectations in terms of their apparent age, size, and brightness. The race to make discoveries was intense, with each passing day bringing forth claims of yet another earliest known galaxy breaking records from various research groups. The outcome, as described by Charlotte Mason, an astrophysicist at the University of Copenhagen, was that everyone was freaking out. We really weren't expecting this. In the weeks and months following the JWST's revelations of unexpectedly mature early galaxies, both theorists and observers rushed to offer explanations. They pondered whether the abundance of unusually large and luminous early galaxies might be misleading, possibly due to errors in analyzing the telescope's initial observations. If these findings proved to be authentic, could they be reconciled within conventional cosmological frameworks? Alternatively, might they signify the initial indications that the universe harbors greater strangeness and complexity than our most audacious theories have dared to propose? At the core of this inquiry lies nothing short of our fundamental comprehension of how the ordered universe we inhabit arose from the ancient chaos. The initial discoveries by JWST have the potential to reshape the introductory narratives of cosmic history, encompassing not only ancient eras and distant galaxies, but also our very presence within the Milky Way. According to JWST scientist Mark McCaughrean, a senior advisor for science and exploration at the European Space Agency, the purpose of building these machines is not merely to validate existing paradigms, but to challenge them. The true excitement lies in not knowing how they will challenge our understanding. One could argue that JWST's observations of early galaxies have been in the making for billions of years, but in a more humble sense, their origins can be traced back to the Space Telescope Science Institute, STSCI, in 1985. At that time, the launch of the Hubble Space Telescope was still 5 years away, but Garth Illingworth, then the deputy director of STSCI, was taken aback when his boss, the director at the time, Riccardo Giacconi, who passed away in 2018, tasked him with contemplating what would come next after Hubble far into the future. I remember objecting, mentioning that we already had plenty to focus on with Hubble. Illingworth reminisced, but Giacconi remained adamant. "Believe me, this will require considerable time," he assured. So Illingworth and a small team began brainstorming, outlining conceptual designs for what eventually evolved into the Next Generation Space Telescope, NGST, later rebranded as JWST in honor of a former NASA administrator. Hubble was expected to bring about significant changes, yet astronomers were aware of its constraints due to its focus on observations in visible light. When light from a distant galaxy traverses the vast cosmic expanse, it undergoes stretching caused by the expansion of the universe, leading to a phenomenon known as redshift, where wavelengths are broadened. The extent of this redshift value indicates the degree of stretching the light has undergone, thus indicating the distance of its source galaxy. The redshifts of early galaxies are incredibly high, causing their originally emitted visible light to stretch into the infrared spectrum by the time it reaches our telescopes. This is the reason why Hubble couldn't detect them. On the other hand, The NGST would operate in the infrared spectrum and would feature a significantly large and cold mirror for gathering starlight. This capability would enable it to delve much further into the universe than Hubble. Everyone understood that Webb would serve as the go-to telescope for studying early galaxies, Illingworth explained. That quickly became its primary scientific objective. The urgency for such a telescope was underscored in December 1995 when astronomers directed Hubble towards what appeared to be an empty area of the sky for 10 consecutive days. Many experts doubted the value of this prolonged observation, expecting it to yield only a few faint galaxies at best. However, the outcome exceeded expectations, proving to be immensely fruitful. The outcome, known as the Hubble Deep Field, revealed that the seemingly empty space was teeming with thousands of galaxies, spanning a period of 12 billion years in the 13.8 billion year history of our universe. Galaxies were everywhere, remarks Illingworth, currently an astrophysicist at the University of California, Santa Cruz. The Hubble Deep Field unveiled a bustling and enthralling early universe, surpassing the expectations of most and presenting observational delights to those who dedicated the time and effort to examine it thoroughly. However, despite the remarkable achievement of the Hubble Deep Field, astronomers yearned for further advancements. Following over 2 decades of intensive work and an investment of approximately $10 billion, JWST was finally launched on Christmas Day 2021. A month later, the telescope reached its designated deep space location, undergoing rigorous testing to guarantee its peak performance. By July 2022, it was primed to embark on its eagerly anticipated inaugural year of scientific observations, referred to as Cycle 1. During the initial phase, a portion of the telescope's time was allocated to significant programs spanning various fields, with data promptly shared with the public. Among these surveys were the Cosmic Evolution Early Release Science Survey, CEERS, and GLASS, the Gravitational Lensing Amplified Survey from space, both of which dedicated numerous hours to the exploration of galaxies independently. In the early stages, when focusing on distinct sections of the sky, expectations were modest, perhaps anticipating a slightly enhanced rendition of the Hubble Deep Field, but not much beyond that. Stephen Finkelstein from the University of Texas at Austin, who leads CEERS, explains that the emergence of extremely distant galaxies was projected to occur only after several cycles of data collection from various programs. However, astronomers were taken aback when extremely distant galaxies appeared right away. Hubble's previous record for the most distant known galaxy was GNZ11, discovered in 2015 with a redshift of 11. This milestone was achieved following a 2009 upgrade that improved the telescope's limited infrared capabilities. A redshift of 11 corresponds to a cosmic age of approximately 400 million years, a period believed to mark the onset of galaxy formation. However, right from the initial GLASS data, 2 separate teams, led by Naidu and fueled by an exhilarating late-night revelation, independently detected GLASS Z13 at a redshift of 13, pushing back the cosmic clock by approximately 70 million more years. In their pursuit of rapid outcomes, the researchers depended on redshift estimates calculated from straightforward brightness-based assessments. While these methods are simpler to execute, they are less accurate compared to direct redshift measurements, which demand more focused observation periods. However, despite its simplicity, the simplified method proved to be reliable, pointing to a galaxy that was surprisingly luminous and substantial. It already possessed a stellar mass equivalent to 1 billion suns, albeit a few hundred times less than the stellar population of the Milky Way, despite the latter being billions of years older. This exceeded even our most hopeful expectations, remarks Tommaso Treu, an astronomer from the University of California, Los Angeles, and the lead researcher on glass. However, this record didn't stand for long. Over the subsequent days, numerous potential galaxies identified by Sears and Glass emerged, boasting estimated redshifts reaching as high as 20, merely 180 million years post-Big Bang. Some displayed disk-like structures, a surprise given their early appearance in cosmic chronology. Concurrently, another research team uncovered indications of galaxies comparable in size to our Milky Way, at a redshift of 10, less than 500 million years after the Big Bang. The swift appearance of such colossal entities challenges the predictions laid out by the standard cosmological model known as lambda cold dark matter, LCDM. This model integrates scientists' most refined assessments of the characteristics of dark energy and dark matter, which together play pivotal roles in shaping the formation of vast cosmic structures. In this context, lambda represents dark energy, while CDM denotes cold dark matter, which moves relatively slowly. If you were to gather all available materials for star formation and instantaneously trigger their assembly, you still wouldn't achieve such enormous sizes at such an early stage, explains Michael Boylan-Colchin, a cosmologist at the University of Texas at Austin. It would truly revolutionize our understanding. To grasp the complexity, let's revisit the basics. In the initial moments following the Big Bang, our universe was an incredibly hot and dense mixture of fundamental particles. Over the subsequent 3 minutes, as the universe expanded and cooled, helium nuclei and other lightweight elements began to form. Fast forward 400,000 years, and the universe had cooled sufficiently for the first atoms to emerge. When the universe reached about 100 million years old, theorists suggest that conditions became conducive for the birth of the first stars. These colossal spheres, primarily composed of hydrogen and helium, lacked the heavier elements found in contemporary stars, resulting in distinct characteristics. Larger and brighter than stars today, these early suns aggregated into proto-galaxies, clusters of gas clinging to expansive, invisible frameworks of dark matter, steered by the force of gravity. The subsequent merging of these proto-galaxies gradually gave rise to larger galaxies. This transformative process, converting the early universe's disorder into the structured cosmos we now recognize, is estimated to have taken approximately 1 billion years. However, JWST's revelation of luminous galaxies in the early universe challenges this narrative. We would expect to observe numerous small proto-galactic fragments that have yet to amalgamate into larger galaxies, explains Stacy McGaw, a cosmologist at Case Western Reserve University. Instead, we're observing a few entities that are already substantial galaxies. Some of these galaxies may be deceivers, closer galaxies concealed by dust, which dims their appearance and makes them seem more distant when assessed through brightness-based measurements. Nonetheless, subsequent observations of Glass Z13 in August 2022 by the Atacama Large Millimeter Array, ALMA, in Chile suggested otherwise, as ALMA did not detect substantial amounts of dust. I believe we can dismiss the possibility of lower redshift intruders, states Tom Bax, an astronomer at Nagoya University in Japan, who led the observations. However, due to the absence of dust, ALMA faced challenges in detecting the galaxy, highlighting the difficulty telescopes may encounter in validating observations made using JWST's advanced capabilities. Naidu expressed, "The upside is no detections were made," he remarked. "The downside is no detections were made. Only JWST has the capability to independently follow up on these observations." One intriguing possibility is that the current standard cosmological model, known as LCDM, may be flawed and necessitate re-evaluation. Boyle and Kolchin remarked, "These findings are incredibly surprising and don't neatly fit into our accepted cosmological framework. It's not just a minor adjustment. It could mean revisiting our fundamental assumptions." A controversial theory, modified Newtonian dynamics, MOND, suggests that dark matter isn't real and proposes that gravitational effects attributed to it are instead caused by large-scale variations in gravity. JWST's findings might lend support to such a concept. MOND has seen many of its predictions validated, and this seems to be another instance, remarks McGaw, a prominent advocate of the theory. However, there are skeptics. Thus far, MOND hasn't provided satisfactory explanations for the tests we've conducted, explains Jehan Kartaltepe, an astrophysicist at the Rochester Institute of Technology. A simpler explanation could be that early universe galaxies possessed minimal or no dust, resulting in brighter appearances. This circumstance might complicate efforts to accurately assess their masses and could potentially elucidate why ALMA struggled to detect Glass Z13. It's possible that supernovae hadn't yet produced sufficient dust, or perhaps dust was expelled from galaxies during their initial formation stages, suggests Andrea Ferrara, an astronomer at the Scuola Normale Superiore in Italy, who has proposed this theory. Alternatively, Mason and her colleagues propose that JWST, in its observations of the early universe, may be primarily observing the brightest young galaxies, which are naturally easier to detect. There could be some unique phenomena in the early universe that facilitate easier star formation in certain galaxies, she speculates. David Spergel, a theoretical astrophysicist and the current president of the Simons Foundation in New York City, concurs. What we seem to be observing is that the formation of high-mass stars is remarkably efficient in the early universe, he explains. The gas pressures and temperatures are significantly higher, profoundly influencing the conditions for star formation. It's plausible that magnetic fields emerged earlier in the universe than previously assumed, potentially catalyzing star formation. We may be witnessing an indication of magnetic fields emerging very early in the universe's timeline, Spergel suggests. The swift influx of scientific papers following JWST's initial observations isn't coincidental. When the initial data began arriving, astronomers were eagerly anticipating it. Many had been refining their analytical methods for years, notes Boyle and Kolchin. Instead of adhering to the traditional peer review process, which often spans months, astronomers opted to share their findings on platforms like Archive, a website where scientific papers can be uploaded with minimal review by moderators well before formal peer review. A new form of near real-time peer review unfolded on social media platforms like Twitter. It's the era of archive science, remarks Naidu. The ensuing excitement was both intense and unexpected, says Nancy Levinson, interim director of STSCI. I anticipated a considerable amount of activity, but I underestimated its magnitude. As a result, discoveries could swiftly be disseminated and debated, yet some worry this came at a price. People were perhaps rushing things a bit, notes Klaus Pontoppidan, JWST's project scientist at STSCI. The gold standard remains a peer-reviewed paper. Early calibration issues with JWST, for instance, might have influenced certain findings. Nathan Adams from the University of Manchester and his team discovered significant discrepancies, with one galaxy initially pinpointed at a redshift of 20.4 later recalibrated to just 0.7. We need to exercise caution, Adams advises. It's premature to claim we've completely upended our understanding of the universe. However, such challenges are unlikely to eliminate all of JWST's high redshift galaxies, given their abundance. It's more probable that the early universe diverges from our predictions, suggests Finkelstein. The likelihood of all of us being mistaken is slim. Astronomers are currently in a race to conduct follow-up observations with JWST. Levinson reveals that she's currently evaluating around a dozen proposals from various groups requesting additional JWST observing time, most of which aim to scrutinize high redshift galaxy candidates. Considering the excitement and significance of these initial discoveries, we felt it was justified to request some extra time to verify them, explains Treu, who submitted one of the proposals. Several other initiatives are now poised to search for distant galaxies, such as Cosmos Webb, overseen by Kartaltepe, which is anticipated to significantly expand the known population of early galaxies by observing a broader expanse of the sky for hundreds of hours. We anticipate detecting thousands, she asserts. Additionally, future projects may seek evidence of the first proto-galaxies, possibly utilizing the explosive demise of supersized initial stars and exceptionally luminous and energetic supernovae as indicators of their existence. Some projections suggest that JWST could peer as far as a redshift of 26, merely 120 million years after the Big Bang, an astronomical blink of an eye. Much effort will also be devoted to following up on the burgeoning roster of high redshift candidates. Even confirming a handful of these would be truly remarkable, notes Naidu. It would validate that we're not being misled. Thank you for watching. If you enjoyed this video, don't forget to give it a thumbs up and hit that subscribe button for more content like this. Stay tuned for our next upload by turning on notifications. And if you want to support our channel even further, consider becoming a member or checking out our merchandise store linked in the description below.